Hello students, welcome to the Champion series. I am your Anushka ma'am and I am here with yet another amazing session. So my dear students, today we are going to cover metallurgy. One of the most interesting chapter, as I say always for every chapter as well, right? Yes. So I am going to make this chapter interesting for you. I guarantee this. What you have to do is attend this complete session, my dear students, and try each and every question which we are going to discuss. See, everyone has a little bit fear from metallurgy. I know that. But my dear students, it is actually an amazing chapter. It has concepts. If you are going to listen this very thoroughly, just try to make a story in your mind that how a particular process takes place, and metallurgy would be like so easy for you that you will never face any problem in this particular chapter. So my dear students, let us start this chapter. So when we talk about metallurgy, what exactly is metallurgy? See, why do we need metals? Yes ma'am, we need metals for various n number of things, right? Yes, you need metals. Now my dear students, have you ever thought how these metals are actually extracted? They are extracted by various processes, and those all processes are involved in the metallurgy. Yes, actually this is a chapter which has practical applications which you can see all around yourself. What a scientist does is he actually thinks of ways how can you extract a metal. You know that metals are naturally occurring. Yes ma'am, they do occur in the nature in various forms. Now they are not alone, they are as mixed with various other factors, things as well, various other elements which we term as impurities. Yes ma'am. So from that mixture you need to extract that metal, right? Yes. And for that you need techniques. Yes, you need scientific techniques, and at the same time you need those techniques to be economically, financially very easy, or I would say that you want something to be economical, right? Yes ma'am. So what metallurgy would tell you is that how can you be a scientist, how can you extract a metal, and how can you do that economically. So we are going to actually find out different ways of extracting different types of metals, and that too economically. So our major concern would be on economical extraction of various metals. Not only extraction could be done in any way, right? Yes, there are, like for each extraction there could be thousands of ways, but you have to find, being a scientist, you have to find the most economical way to extract that metal, and that is what is known as metallurgy, right? So we are going to discuss everything about this. Now the next question is, I know various metals are present in the atmosphere, various metals are present in on earth in various different forms. So the major part where the metal actually exists is known as mineral. What it is known as? It is called mineral. In mineral you have the metal as well as various elements, other elements mixed with it, right? Yes. So what is a mineral? A mineral is a form where a metal is present, but you don't know that you can extract that metal economically from that mineral or not. Okay. Now the form of mineral from which the metal can be extracted economically, a sufficient amount of metal you can extract from a particular mineral, then it is known as a ore. This means that you will have, just a second, this means that you will have mineral. Yes ma'am. In mineral you will have the metal which you want to extract with the other elements present. Those will be obviously impurities. Now there are two possibilities. You start extracting the metal, right? Yes. Either you will get sufficient amount of metal or you will not get sufficient amount of metal, right? Yes, using the various techniques. Yes ma'am. So the part where you could extract the sufficient amount of metal, that would be known as a ore. Means a ore is actually a mineral from which the metal can be extracted economically at a very, not only economically, metal could be extracted in sufficient amount. That would be known as ore. But the mineral from which you cannot extract the metal in a sufficient amount, that will not be considered as an ore of that particular metal. Okay, yes. So I can say that every ore is a mineral. Obviously, because when you talk about ore, it comes from minerals only, right? First it will be a mineral, only then you will have a possibility of extracting it in sufficient amount. But can I call every ore a mineral? Every ore, every ore is a mineral, I can call that. Can I call every mineral that every mineral will be a ore? No, ma'am. Might be that you are not able to extract that metal, right? Yes. So every ore is a mineral, but every mineral may not be a ore. May not be a ore. Okay. So now let's see the actual scientific definitions of the two. I hope the concept is clear to you. Now we can see the definitions. Perfect. Let's move. The natural material in which the metal is found in nature is called mineral. It is the natural material in which it is found in nature. Yes, you can extract or you cannot extract. The other type is ore. Those minerals, see, those minerals from which the metal can be extracted conveniently, economically, and in large quantity are called ores, from which you can extract in large quantity economically as well. That is known as ore. So, thus, all the ores are minerals. All the ores are minerals, but all the minerals are not ores. Right? Yes, ma'am. Clear, my dear students? I hope this is clear. Now, in metallurgy, you have only a few types of metals which you need to study. You are not supposed to study all the metals. There are only a few metals which you need to study. And again, I would say for this particular chapter, you need to read the NCERT, my dear students. It is the base. You only need to study those metals which are there in NCERT. Nothing beyond that is ever going to be asked from you. Okay? Yes. So this was a disclaimer. You have to read NCERT. Let's move forward. Now, when we will discuss this, you will have those metals basically differentiated or classified, I would say, in 4 major types. Actually, those are 5, but I would involve the first and the second type in the same one. Okay. There are 4 major types. Let us say type 1. Then there would be type 3. I would say type 1 and type 2 would be here. Then type 3, then type 4, and then you will have type, okay, you will have type 4, yeah. So now, what I want to make you understand is that you have different types of metals. The type 1 and type 2 actually consist of the most reactive metals. This is most reactive. These are very reactive metals, okay? I'll give you the names of the metals as well, but now right now you need to just understand this. Type 1 and type 2 are actually the most reactive types of metals. Okay, yes. When you come to the type 2, type 3, type 1, type 2, type 3 and type 4. Okay, then here will be type 5 as well. Now, when we talk about type 3, you have discussed about the most reactive. Now, only the reactive, not most reactive, reactive. They are moderately reactive. So, you could say that these are moderately reactive. Then, you will have what type of metals? You will have less reactive metals. And then you will have the least reactive. Okay. I'll give you the examples as well. Don't worry. What I want to make you understand here is that when you talk about the type 1 and type 2, which are the most reactive forms of metals, they are generally found in the nature as their chlorides, carbonates, or sulfates. Okay, so what do I mean by this? That the type 1 metals will either be present in form of the metal chlorides, or in form of metal carbonates, or in form of metal sulfates. Okay, yes. Now if you talk about the type 3, which is your moderately reactive metals, they are generally present in the form of their oxides. Sorry, these are present in the form of their oxides. Okay, yes. So you will see that the third type of metals, which are moderately reactive, they'll generally be present in the form of their oxides, like the metal oxides, right? Yes. Next, when you talk about the fourth type, which is less reactive, these metals are actually present in the form of their sulfides. These are actually present in the form of their sulfides. Okay, so you will think, you will talk about them as metal sulfides, right? So all these least reactive, like if I talk about the less reactive metals, like copper is a less reactive metal, yes ma'am, and that will be present in the form of its sulfides, form of Cu2s. Okay, yes. Now when you talk about the least reactive types, my dear students, the least reactive are actually present in their elemental form. These are actually present in their elemental forms. Okay, they are not present in the form of metals, oxides, sulfides or sulfates anyway. It is actually present in its elemental form, and you can extract it directly. Okay, so this is the basic gist of your metallurgy. Okay, now once you will get the metal, you know that they are generally present in these forms, then accordingly you will apply the scientific techniques and you can extract them. So this is the general idea. Now we are going to study about them. Perfect, my dear students, let's move forward. Now, what is the metallurgical process? Extractive metallurgy is a scientific technique employed for the extraction of metals economically. Very important, my dear students, economically on a large scale from their respective ores. Okay, now let's talk about the type 1 metal. I just told you type 1 and type 2 are together. Okay, the most reactive ones. These are very electropositive, very reactive metals found as soluble salts. For example, they are generally present as chlorides, carbonates and sulfates. Yes ma'am. The metals are extracted by electrolytic techniques. These are generally extracted by which techniques, my dear students? Electronic techniques. These are important questions which would be asked from you, right? So you need to take care. Perfect. Next, we are going to talk about the second type. These are again the electropositive metals, mostly the alkaline earth metals. See, the most reactive one, the most electropositive one are S block metals. Yes, group 1 actually belongs from here. This group would be group 1 metals, alkali metals, and group 2 is from type 2. I hope it's clear now. Found principally as insoluble carbonates. See, these are also present in carbonate form. I told you type 1 and type 2 could be present in carbonate form or sulfate forms, right? Right, yes. But these actual carbonates were soluble, but the alkaline earth metal carbonates are insoluble. So it is very important that these are insoluble carbonates and sulfates. Clear. Magnesium sulfate is soluble. This is an exception. So we can mark it as exception, which you need to remember, and I hope you remember this when you might have studied this in your S block chemistry as well, that why do magnesium sulfate is soluble? Because of its diagonal relationship, right? Yes, I hope you remember this part. Perfect. They are extracted by electrolysis. Again, these are also extracted by electrolysis the same way as these are extracted. That is not a problem, but you need to remember that these have insoluble carbonates and sulfates, and the type 1 has actually soluble carbonates, and type 1 belongs to group 1 and type 2 belongs to the group 2. Okay, so I'm trying that you just revise everything right in the class. Now let's move forward. Now when we discuss about the type 3 metals, the main sources of these metals are oxides. I told you type 3 is actually present in the metal oxide form. It is present in oxide forms and mixed oxides. Perfect, no issue. A variety of methods are used to extract these metals, including electrolysis. Now, what methods are used to extract them? Obviously, you have oxides. You can use electrolysis process. That is one way. The other way would be through reduction. Okay, so I will tell you how reduction takes place, but now let's discuss this. And chemical reduction with chemical reduction with carbon, carbon monoxide and more reactive metals. Here we will also study about the Ellingham diagram. Okay, yes. Now let's move forward. Type 4 metals. These metals occur principally as sulfides. I told you type 4 actually is present in the form of sulfides, and less frequently as oxides. A few of them are present as oxides, but mostly in general we would say they are present in the form of sulfides. The sulfides are almost always converted to oxide. First, the sulfides would be converted into oxides, and then you will reduce them using some reducing agent. So what can you say? That these metals would be present in sulfides. You will convert them to oxides, and after oxides, you know what you did here? You did reduction, right? So you will do their reduction and you will get your metal. Right? Yes. So prior to reduction with carbon, carbon monoxide, and in some instances hydrogen or sulfates for subsequent electrolytic treatment. Right? In metallurgy, I can only give you a general idea. Obviously, there would be different steps, but the general idea is this. Perfect. Now let's move forward. Type 5 metals are the least reactive one. Okay. These are the unreactive metals. I told you least reactive or unreactive, and occur in the free state. I told you elemental form, free state, or as easily reducible compounds. And so the reduction of these types of metal is the easiest. Perfect? Yes. This was the general idea. Now let's move forward. Now, here is a table. Right? Yes. Now I am going to tell you, I am just going to give you a little idea. I cannot just specify you that these are the type 1, these are the type 2, and these are strictly type 1, type 2, but you will actually get an idea that which lot of the part of periodic table could be considered as reactive, and which lot of the periodic table can be considered to be least reactive. Okay? Yes. So I told you this is the group 1 part, this is the group 2 part. So this is type 1 and this is type 2. These are the most reactive parts, right? Most reactive ones. And when we talked about the most reactive ones, we knew that these were most electropositive and these were present as their carbonates, sulfates, and chlorides, right? Yes. So we are just revising here. Now if you talk about this part, I'll make it with the, let's say, blue color. So when you talk about this part, this part is your type 3, my dear students. And when you talk about the type 3, this is the moderately reactive part, and moderately reactive part is generally present as its oxides. These are generally present as its oxides, and we reduce them using a reducing agent. I hope that's clear. Now, when you talk about the type 4, my dear students, type 4 belongs somewhere here. Right? This is type 4, which is less reactive. You get copper part as well. Sorry. Just a second. I'll make it with a different color so that you'll understand. I'll make it with red. We can generally give this as a part. This will be your type 4. Okay? This will be your type 4. Now, if I talk about the type 5, then the left one part is your type 5. Okay, this is your type 5. This is not strict, my dear students. Obviously, the elements at the borders could be of the different forms. They could go into type 5 and type 4 as well. But this is the general idea. See, in metallurgy, you have to get a general idea. You cannot be strictly saying that this will always be present as its sulfides. You can get them as oxides as well. Okay, so but this is a general idea which will make metallurgy a little bit easier for you. So I hope you have understood till now. We've only discussed the different types of metals. Now let's move forward. These are some of the metals which we are going to discuss. Again, my dear students, I hope you understand this, that these are your reactive ones till magnesium. Till magnesium, it is reactive one. So these will be present as chlorides, carbonates, and sulfates. Right? Yes, I'm not writing it again and again. I hope you understand this. Now when you talk about aluminium, zinc, and these all these are generally present as in the form of what? Type 3 were present in the form of, I hope you remember it, oxides. Yes, so these are present as their oxides. And then you talk about these are present as their sulfides, because these are less reactive, and these are present in the free state. Okay, I hope you got the idea. Perfect. Yes, ma'am, we've got the idea about this. Now, it is very easy, my dear students. What will be the process? Obviously, you will first, and the most important thing is you will find out which is a ore, right? So, first step would be getting a ore. After getting a ore from which you can extract the metal economically, what will be your step 1? I'll write here step 1. My dear students, your step 1 would be you have to extract a metal. What do you want? You want a solution or a mixture where the metal's concentration is very high. So the first process would be concentration. The first process is is called as What has happened to my spellings, my dear students? The first method is your concentration. Okay, what does concentration means? It means increasing the amount of your metal, in the mixture, and actually removing all those dust particles, sand particles, all those things which you don't need. So you will try some methods where you can extract the metal out of it, right? Yes, and the excess of sand and all, you can just remove them. That is involved in the concentration process. Now, once you've done the concentration, still obviously you have to extract the metal, right? Yes, ma'am. So the second step after concentration of the metal, you will extract the metal, right? Yes, ma'am. So the second step would be your extraction of metal. And what would be your third step, my dear students? Ma'am, once we have removed all the sand and all, we've increased the concentration of the metal, we have extracted the metal, we've tried to purify, we've tried to remove all the impurities. Third would be your purification. What is purification? Yes, now you think that your metal is, you have removed everything, but still there would be some minute impurities left. Yes, everything has impurities. So my dear students, here you get purification. So here you have to purify it once again, so that the small amount of impurity still left should also be removed. So there are only three steps, right? You get a ore, what do? You concentrate it, you try to increase the metal concentration in the mixture, then you remove all the sand and all, which is the extraction of metal. And what is the third process? When you think that you have extracted the metal, you need to purify it once again, right? Yes, so the third step would be purification. Only these three steps are to be followed for every metal extraction. Okay, so now what are we going to do? We are first going to see various steps for concentration. Then we are going to study few steps of extraction of a metal, and then we are going to see the few steps of purification, and your metallurgy would be done. This is what is metallurgy, my dear students. So let's start. So now, when we talk about the various forms of ores, in which the metal could be present in the nature are here. If you talk about aluminium is generally present as bauxite, and here is the formula of your bauxite. Next, if you talk about iron could be present as kaolinite, a form of clay. You have iron's formula here, you have hematite formula here, you have magnetite formula. My dear students, you have magnetite formula this, and you have siderite formula this, and you have iron pyrites. Just a second. There is some issue. Yes, no. It's perfectly correct. Iron pyrite. Yes. Perfect. Yes. Now, if you talk about the various forms of copper, you have copper pyrite malachite, and you have cuprit. You have cuprit, which is this form, and then you have, I'll make it with green, you have copper glance, which is this Cu2S. If you talk about zinc blende or sphalenite, this is zinc sulfide, then you have calaminite, and then you have zincite. Okay. This table is actually present in NCERT as well. And yes, my dear students, you need to remember the formulas. You need to remember the formulas of the different ores. I am sorry, but you have to do this. Okay. Yes. So if you are finding this difficult, don't worry. This table is taken from NCERT. There might be some, I don't think there is any error in the formulas, but still you can go through the NCERT table as well. Okay. Yes. Now let's move forward. First question. Obviously, I have told you something, so I am going to ask you a question as well. Okay, so what is the question? The question is, predict the modes of occurrence of the following three types of metals. Highly reactive. How are you going to extract metal if you have very highly reactive metal? I hope you remember this, that ma'am, when you talk about highly reactive metals, you are actually talking about the alkali metal, for example, sodium. This means that these are present in the form of their chlorides, carbonates and sulfates, and these were removed by electrolysis, right? I hope you don't have a issue. We have studied this. Perfect. Let's talk about the other part. When you talk about moderately reactive metals, moderately reactive metals are actually present in the form of their oxides. Yes, ma'am, these are present in the form of their oxides. And when we talk about oxides, how were we going to extract metal? I told you, when you have oxides, you actually involve what? You need reduction with carbon, with coke or carbon monoxide. So you could say that we use reduction processes with coke or carbon monoxide, right? Yes. Next is your noble metals, my dear students, which are actually present in their free state, right? So these are present in free state. So their extraction is not an issue. They can be extracted themselves as well, right? Yes. So these are present in free state. So there is no as such process which is involved. These can be extracted in the form of which they are present. Perfect. Yes. So I hope we've answered all the questions. You don't have an issue till now. You have revised everything. Now let's move forward. When we talk about the other question, just a second, my dear students. We will discuss this question. First, we have to talk about this. Okay, so we'll just do this. This question should be present somewhere here, I guess. Yes. No. This is not a question. I just thought that. Okay. Now, let's move forward. When we talk about the process of extraction, I told you the basic idea of extraction, but there are very, very specific techniques for the extraction. So now we are going to talk about those. The process of extraction of metal from its ore is called metallurgy. Perfect. We don't have an issue. Metallurgy involves the following 5 steps. You have actual 5 steps for extraction of metal. The first step is concentration. I told you, dressing, concentration, right? You increase the concentration, which is also known as dressing. Then you have roasting, then you have smelting, then you have reduction, and then you have purification. All these 3 actually involve what? Extraction of metal. All these 3 are involved is actually the part of extraction of metal. Okay, the 3 steps which we discussed in extraction of metal, you either do roasting or you do smelting or you do reduction. Okay, yes, so we will talk about these in detail. Perfect. Now let's move forward. The first and the most important is your concentration, which is also known as dressing, which is also known as with one more word, which is your leaching. We'll discuss about it. Now see what is concentration, increasing the amount of the metal. See, ores obtained from the mines often contain non-metallic and rocky materials such as sand, clay, silicates, feldspar, etc. Obviously, whenever you think about a ore, there would be hundreds of other things also present. Now, these impurities are called gangs. These impurities are known as gangs, and you need to remove this gang to increase the concentration of the metal. Yes, ma'am. Or matrix. Okay, these 2 names are going to be used again and again, so you need to know this. Now, the process of removing the gang of thereby increasing the concentration of metal in the ore is called concentration of the ore. It is known as the concentration of the ore, right? I hope you understood this. You've got the technical definition as well. Now let's move forward. Now, the first process of concentration is gravity separation. Now, my dear students, the various steps that are involved depends on the physical properties of your metal. Whether a metal is heavy, whether its impurities are light, right? we talk about the density. Or it may be that the metal is actually magnetic in nature and the impurities are not magnetic in nature. Then we can remove them with different other ways, right? So the techniques which will be used for the concentration will actually depend on the physical nature of your metal. Okay, so the first is your gravity separation. When you talk about gravity separation, what happens is you actually have you have your metal and you have your gangue, which is your impurities. Now there will be a possibility that either your metal is heavy or your impurities are heavy. So what does happen in a gravity separation method? You have something like this, a sloping thing you have, and what you do is you fill your crushed, you take your ore, you crush it, right? You crush it, and here water is flowing, right? On this slope water is flowing. Now what will happen when you will pass your crushed ore through it? The water will actually take the, let us say that density of your gangue is less than the density of your metal. So the one which has less density, will move fast. I hope you understand this. Yes, ma'am. So what will happen when you pass this ore through water? Water will take away the gangue first because its density is low. It will just move fast as compared to your metal. So you can just remove all the gangue, all the impurities, and then you can get your metal. Obviously few gangue still will be left, and that is what will be removed in the purification process. Okay, yes. So what is your gravity separation? Now we are going to discuss this. The ore is powdered, you powder the ore, then it is then washed in running stream of water. I told you the lighter earthly materials and the gangue are washed away. Those are lighter, they have a low density, they have low gravity, since they have low density, so they will move fast, right? Yes, away, while the heavy ore particles remain behind. The oxide ore of iron. Now you need to remember that which type of ores actually are removed in this particular way. So the oxide ore of iron, and which is Fe2O3 and Fe3O4, are concentrated by this method, and this method is also known as lavigation. There are two names for this method, lavigation or gravity separation. So what does in gravity separation happens? You have a slope where you put your crushed ore and it gets washed away with water, and since the impurities have a lower density, they flow first and you get your ore later. If somehow there is any ore in which your metal ore's density is less and the impurities density is more, then you can remove the metal first. It will move with water first and then your impurities will come. So this is the way you can remove the ore from its impurities in the gravity separation method. You need to remember that which method is actually used for various different ways, and there could be two different techniques used for the same ore as well. Okay, so don't get confused. So ma'am, we understood Fe2O4, Fe3O4 and Fe2O3 are the ores which could be removed by gravity separation method, right? Perfect. So this is the setup, if you need to know the setup as well. Okay, now let's move forward. Next is your froth flotation process, a very important process, and it is generally involved for the sulfide ores. I'll give you the gist of the process and then you can study the process from the theory. We don't have a picture? Yeah, we have. Okay, see what happens is, let us consider you have a particular sulfide ore. You have some sulfide ore, let's say you have PBS, you have this ore. Okay, obviously it will have some impurities as well. What do you do? You actually put some oil into it. Okay, so what did I do? I did put some oil to it. Now, what will this oil do? My dear students, this oil will actually, just a second. This oil will actually surround your sulfide ore. This will actually surround your sulfide ore. And you will add water in this mixture as well. Now, you have, first you took a powdered form of this mixture, impurity plus your ore. Yes, you added water to it and you added this palm oil. Let us say it is eucalyptus oil or palm oil, and you added the oil into it. What will happen? The oil will preferentially surround your sulfide ore and it will not do anything to the impurities. Okay, ma'am. What will happen? Now, since this oil has covered the sulfide ore, it will not come in contact with the water. Yes, ma'am. So it increases its non-wettility. It will not let it wet. Perfect. Yes. Then you actually mix the solution. You mix the solution with this stirrer. You mix the solution, and when you mix the solution, what happens? Froth is formed. What is formed? Those bubbles, froth, which whenever you wash your clothes, you get some froth, na? Bubbles. Yes, that is formed. Now, what will happen? This froth will take these sulfides up since they are lower in density. So these froth will take the sulfides up and your impurities would be left down. And this is how you can separate your metal from the impurities. Perfect. This is the major gist of the process. Obviously, there are very many different things as well. We will talk about them as well. So now I have given you the gist. Here is the froth. This is your froth. I'll write it with dark blue color. This is your froth. Perfect. Here, this is the paddle with which you stir the mixture. Okay, so I hope you've got this. This is the rotating paddle. Now let's see what the theory says. In froth flotation process, mostly employed for sulfide ores. So all the sulfide ores can be purified, can be concentrated by this method. I hope it's clear. Water is mixed with 3.5% by weight of eucalyptus oil. I told you eucalyptus oil will surround the sulfide ore. Yes, ma'am. Or some other cheap oil, and the mixture is stirred by compressed air. It is stirred by compressed air. Shown in the figure, froth is generated, I told you, at the surface. Sulfide particles in the ores are preferentially wetted by this froth. This froth actually takes your sulfide ores and rise to the surface. They are skimmed off by a skimmer. There is a skimmer which takes away the froth as well as your ore. Gang is preferentially wetted. What is gang? Your impurity is preferentially wetted by water. I told you it will be wetted by water and it sinks to bottom. Reagents employed in froth flotation are of 4 types. There are 4 different types of reagents used in this process. What are those? First is your frothers, which create the froth. The first is the frother, which actually creates the froth, which you use the oil. You use different types of oils. They are actually your frothers. They are named as frothers. So what are frothers? Which create froth, the oil which you added, which increased the non-wettility of your sulfide ore. Next is your collector. Which help in attachment of ore particle to an air bubble in the froth. There are some collectors which you add, such as your sodium xanthates or benzene. These, what did they do? They actually connected the ore particles. They actually connected the ore particles to the froth. Okay. Yes. So which helps in the attachment of the ore particle to the air bubble in the froth. You have an example which is sodium xanthates. You need to remember the name. Okay. Yes. I hope it's clear. Now, when you talk about the third, it is activators. Simple inorganic compounds which increase the effect of collectors. It increases the activity, which is an example is Na2S. This is basic, right? Next is your depressants, and it is very important. Why is it important? Now, one thing I told you, that if only one sulfide ore is present, you can remove it by this process. What will happen if you have, let us say, PBS and ZNS together? You have 2 different sulfides present in the mixture. Now what will happen? Now you need to use depressants. What do depressants do? They actually depress one of the sulfide, and the other sulfide will form the froth and go upwards. Okay, and then you can remove it. But The other, let us say, I have given you an example, you have PBS and ZNS. What do? You add a depressant to this solution. Okay, so it will depress the zinc sulfide. The zinc sulfide will sit down in the bottom, and this PBS will form froth. And this will move upward, and then you can remove it. So what is the role of depressants? It has a role when you have two different types of sulfides present. Okay, yes. So now let's see which suppresses the flotation of particular selectively. For example, an ore containing PBS and ZNS is floated in the presence of Cn minus. Here Cn minus in the form of KCN, or NaCN, KCN or NaCN. Okay, so KCN or NaCN form, it is added. It depresses the ZNS sulfide. Flotation of zinc sulfide is suppressed and only PBS is removed. Cn minus is then destroyed by using any oxidizing agent, and then ZNS is floated again. So once PBS is removed, then you can use the same process again. My pen just fell down. Just a second, my dear students. Okay, so now what will happen? Since PBS is removed, now you can use the same processes again, and then you can remove ZNS as well. So the depressant's role was to depress one of the sulfide. Perfect? Yes. So I hope you got the process of froth flotation as well. Now let's move forward. This was the setup. I hope you understood it. Perfect. Now let's move forward. Now you have to do a few questions. Which of the following ores is best concentrated by froth flotation method? So my dear students, for this you need to know the ore's name, right? Yes. So I am moving aside. You have to do this question. Try this question. Okay. So now, which of the following ores is best concentrated by froth flotation process? For this you need to write all the ores formulas, right? I know that by froth flotation method, this is actually employed for sulfides. Yes, so I need a ore of sulfide. Okay, yes. So if we talk about malachite, it is CuCO3 dot CuOH whole twice, right? Yes, so it is not a sulfide, so this cannot be your answer. Next, if you talk about this is your cassiterite. Yes, it is SnO2. I hope you get it. It is a oxide. It cannot be employed. Froth flotation cannot be employed here. This is your PBS. And this is magnetite. This is Fe3O4. So PBS. So what can I say? I need a sulfide, and I have got a sulfide, which is option C. So option C will be your correct answer. I hope you got it. Perfect, my dear students. Let's move forward. Next question. Okay. Name 3 ores which are concentrated by froth flotation process. You have to give 3 ores which could be concentrated by froth flotation process, and what is meant by a depressant. So I have told you everything. Now what you are going to do is, I have given you that table. Just go through that table, find 3 sulfide ores. I think you got 2 already. I've discussed 2. You can find some other as well, and you will write 3 ores. Perfect. And then you are going to give the work of depressant as well. So this is going to be your homework question. Perfect. I hope you get it. Now let's move forward. Next question, my dear students. During concentration of sulfide ores by froth flotation process, potassium ethylene xanthate is added. Why? What is the role of this? I think you get that as well. We have discussed the role of xanthates, my dear students. So am I supposed to give you the answer, or you are supposed to give me the answer? You are going to give me the answer again. So this is also your homework question. By doing your homework, you're actually revising what you've discussed. So try to be very thorough with your answers. Now let's move forward. Now the next method is magnetic separation. What happens in this particular process is that you have a setup something like this, and in magnetic separation, what is the most important thing? What is the principle? The principle is that out of your impurities and your ore, one of the two should be magnetic in nature. Okay, Out of the two, both cannot be magnetic, both cannot be non-magnetic. At least one should be magnetic and one should be non-magnetic. Only then you can imply this process. What will happen is that you have your impurity and your magnetic part. Let's say your metal ore part is your magnetic part. What will happen? You put a magnet here. What do? You put a magnet here. So now from here you put the powdered ore. This part is actually moving. Okay, this part is actually moving. So this will take your ore here, and when it comes down, what will happen? The magnetic part will be attracted towards the magnet and the non-magnetic part will not be attracted, right? In this way, the magnetic part will come and reside here, and the non-magnetic part would go far away and land here. So this way you can separate the major part of your magnetic and non-magnetic part, that is, you have removed your impurities and metal ore, right? Yes. So this is your magnetic roller. These are your magnetic particles, finely grinded ore. Now let's see the principle. This process is based upon magnetic properties of the ore and gangue. If the ore of the impurity present is magnetic, then this process is used to separate the magnetic substance from the non-magnetic substance. It could be your impurity or your metal. I hope you get it. Perfect. Now let's move forward. Next is your leaching. What is leaching, my dear students? Leaching is actually a chemical method. It is a chemical method of extracting your metal. Leaching is a chemical method of extracting your metal. In this, what do? You see whether a particular ore is soluble in a particular solvent or not. Okay, so now we are going to study this. In this process, the desired metallic component in the ore is dissolved selectively by digesting the powdered ore with a suitable reagent. Okay, perfect. The impurities are left behind as undissolved residue. You will not get this like this. You will understand it once I will give you an explanation, a story to it. Okay, so what happens is, let's take an example, and this example is actually present in your NCERT, so you have to read this example only. Let us talk about Al2O3. What do I understand by this Al2O3? Okay. By Al2O3, my dear students, it is actually amphoteric in nature. Al2O3 is amphoteric in nature. Oxides of aluminium are amphoteric in nature. They can act as acid as well as base. Okay, yes. So I know that this can act as an acid or it could act as a base. When I talk about the impurities present with Al2O3, there are major two types of impurities. One is TiO2 and the other is Fe2O3. These two types of impurities are present, and I want to tell you that this is also basic in nature and this is also basic in nature. Okay, yes. So, since your impurities are also basic, now you know that if a base reacts with a base, there will be no reaction. If a base reacts with a base, there will be no reaction. Yes, ma'am. If an acid reacts with a base, then there will be a reaction. So, what I did is that I know that my ore is can act as an acid as well as a base. If I bring a base towards it, it will act as an acid. If I bring an acid to it, too close to it, it will act as a base. So I very smartly thought that since these impurities are basic, I'll react my ore with a base. I'll react my ore with a base. If I will take a base, and my dear students, Al2O3 will now act as an acid. I hope you get it. So I will say that this will act as an acid. Now it will act as an acid. Yes, since these two are bases and base doesn't react, so these would be removed. Very easy, my dear students. Yes, that is the reason I reacted it with a base. So when I reacted it with a base, I got NaAlO2 and I got H2O. This is how I have removed major part of the impurities. I have removed the major part of the impurities. Now from NaAlO2, I need my aluminium metal oxide, right? So what will happen? This one was impure. Okay, my dear students, this one part was impure, which had your TiO2 and Fe2O3 in it. So now after reacting this, this is formed and this does not have TiO2 and Fe2O3. I want pure Al2O3. So now what will I do? I will take this NaAlO2 and I will add water to it. And I will add water to it. So I added water to it. I got aluminium hydroxide. I hope there's no issue. And you got NaOH. Perfect. So you got aluminium hydroxide. After this, what did you do? You heated it. You heated it. Okay, you heated it at a very high temperature, and what happened? It decomposed and it gave you Al2O3, which was actually pure. Which was actually pure, right? Yes. So this is how you get pure Al2O3 from impure Al2O3. You very smartly, what did you do? You saw that it is amphoteric in nature, so you used a base so that you could remove the basic impurities. If you had acidic impurities, what would you have done? You would have made it react with the acid so that the acid impurities would be removed, right? I hope you got it. Now if you will read this, you will understand every part. See, in Bayer's process, bauxite, Al2O3 and ore of aluminium is digested with NaOH solution. Now, I hope you understand this, that why is it digested with NaOH solution? Only because the impurities are basic, which dissolves all the Al2O3 component in the ore to form soluble sodium aluminate, and the impurities like TiO2 and Fe2O3 are left undissolved residue. Why undissolved residue? Because they've not reacted, because they were base. Perfect. So this is the reaction what happened. Now, from the aqueous solution of sodium aluminate, aluminium hydroxide is precipitated by adding a little freshly prepared water. My dear students, here adding a little freshly prepared H2O. Okay. Now, this is the reaction what took place when you added water. Now, the precipitation of aluminium hydroxide is concentrated and is ignited to form a pure alumina. And this is how you get this pure alumina. And this is how you get pure alumina. So I hope you got it, how you used the leaching process, where you find out which is the absolutely correct solvent you need to use. Like this, like the reason here you used NaOH. Why NaOH was the correct solvent? Because it was a base. Okay. Yes. So this is what happens in the leaching process. I hope you got this. Perfect. Let's move forward. Now, when you talk about extraction of crude metal from the concentrated ore, now you've concentrated the ore. Yes, now you are extracting the metal. So this is, my dear students, the second step where we were talking about the extraction of the metal. When you extract the metal, how do you extract the metal? There are various different ways. So the first way is your calcination. What happens in calcination is, there are majorly two types of processes, calcination and roasting. We will be talking about both. Calcination means that you are heating some metal. My dear students, but in the absence of air. Complete absence of air, you are heating some ore will give you what? Oxide. Okay, you will get a oxide, but heating in absence of air is known as what? Calcination. So here is the definition. The concentrated ore is heated in absence of air below its melting point. This process is called calcination. So since you have studied the S block chemistry, so I hope you understand that in S block chemistry, my dear students, I hope you know that the carbonates of group 1, actually on heating, they do not decompose, they get melted, right? Yes. So if you will use calcination in case of group 1 carbonates, if you use calcination process, then what will happen? Will they decompose? No ma'am, they will melt. So my dear students, what will you say? That this is not applicable to group 1 carbonates, as they do not decompose but melt. Okay, so they'll melt, they'll not decompose and give you oxide. Clearly you've got this. Now let's move forward. There are a few examples which actually get decomposed and get converted into their oxide, and that is the reason in case of absence of oxygen we can use calcination for them. For example, you have aluminium hydroxide. When you heat aluminium hydroxide, you get Al2O3 in the absence of air. All these steps are taking place in the absence of air. Okay, perfect. So there is this one process. Second is Fe2O3. Fe2O3 will decompose and give you Fe2O3. This is hydrated Fe2O3. This will give you Fe2O3 plus water. Now if you talk about siderite, that is FeCO3. This will heat and this will give you FeO, and this will give you CO2. So what you are actually seeing that you are heating in absence of air, but still you are getting oxides. So the main aim of calcination is getting oxides, but in the absence of air. Now I will tell you about roasting. Okay, perfect. I hope you got this. Why calcination is not applicable to group 1? This question is asked a lot of times, so you need to know the reason. Now let's move forward. ZnCO3 heat, it gives you ZnO. NaHCO3, this is your sodium bicarbonate. I told you that group 1 carbonates, it is not applicable, right? But it is a bicarbonate of sodium. Okay, so it is a bicarbonate. So don't ask me in the comment section that ma'am why you have written this. This cannot be possible. It is a bicarbonate, not a carbonate, my dear students. Okay, so I'll write it. This is a bicarbonate. I don't have a good pen today. Perfect. This is a bicarbonate, not a carbonate. Perfect. Yes. Then calcination. This is a carbonate of group 2. So my dear students, it is a group 2 carbonate, and group 2 carbonates actually decompose. So yes, calcination is applicable to group 2 carbonates, but not to group 1 carbonates. Okay. Yes. I hope you got this. Perfect. Now let's move forward. Next is your roasting. What happens in roasting is, in calcination you were heating in the absence of air. In roasting you actually heat in the presence of air, and the aim of calcination and roasting, both aim is to form oxides, right? But in roasting you heat in presence of air, whereas in calcination you heat in the absence of air. Perfect. So in roasting, the ore is heated in regular supply of air in a furnace at a temperature below the melting point of the metal. Some of the reactions involving sulfide ores are given. And my dear students, most of the sulfide ores, the sulfide ores which we get are actually roasted. Why? Because when you roast them in the presence of oxygen, they will get converted. The sulfide will get converted into SO2, and SO2 is a gas. It will escape into the atmosphere, and you will get your metal oxide. That is the reason sulfide ores are always and always roasted, and carbonate ores, except the group 1 carbonates, all other carbonates are calcinated because they decompose and they give you oxide. But sulfides, what do? They are roasted. Why? Because when you roast them you get SO2, and SO2 is a gas, and it escapes into the atmosphere. So these are the few reasons. You need not remember and learn all the reactions. You need to understand the concept behind the reactions, right? Yes. So I hope you got this point. So these are 3 different types of sulfides. You roasted them in the presence of oxygen, you got SO2 in every case, and SO2 is escaped into the atmosphere. Perfect. Let's move forward. So my dear students, a lot of times a question is asked. A lot of times, before this I'll tell you, a question is asked that you'll have to answer me this question. Why sulfide ores are roasted and carbonate ores are calcinated? Okay, give me this answer. This is again your homework question. So you'll have to answer me this question. Perfect. Now let's move forward. The next process is, my dear students, smelting. Now we are going to talk about smelting. What does smelting mean? The metal is extracted in the form of a liquid. In smelting, my dear students, you extract a metal in the form of a liquid. In smelting, non-volatile impurities are all removed. The impurities which are non-volatile, they are very easily removed. Refracting solids with very high melting. Now I am going to tell you, my dear students, for smelting, refracting funnel is used. I'll write it here, funnel. So see, what happens is, you have a very big container. Do we have a picture here? Okay, we don't have a picture, so I'll just tell you. So something like this. This is a refracting funnel. So what do? You use a refracting funnel. You put all your ore with your impurities into this part. Okay, yes. So now you will heat it to a very high temperature. And for smelting, what is required? The most important thing, the most important condition, what it is, that your impurities should be non-volatile. They should be non-volatile. I hope you get it. Yes, ma'am. They should be more non-volatile. Now, my dear students, your metal is volatile. Yes, but your impurities are non-volatile. So what will happen? You will heat this particular container a lot. Since you are heating it, what happens? What will happen if the container itself gets melted? Everything will be waste, right? So you need a funnel which is made up of such material which has a very high melting point, say 8,000, 9,000 degrees Celsius temperature is their melting point, right? Yes. So refracting funnel is used for smelting purposes, where you add your ore with the impurities which are non-volatile, and you heat them to a high temperature, where what will happen? Your metal will melt. Okay, but your impurities will not melt because they are non-volatile. They'll not go anywhere, right? Yes. So what will happen? Your metal will melt into the liquid state, and you can remove your metal, and the impurities would be left behind because they will be present in their solid states. So this is the gist of smelting. So I hope you will get it. The metal is extracted in the form of liquid. It will melt, and it will be extracted in the form of liquid. In smelting, non-volatile impurities will be removed because those are non-volatile. They will not melt easily. They have a very high melting point. What is refracting funnel? It is made up of such a material which has a very high melting point, because we need such a funnel for smelting purposes, right? Yes. So I hope you get this. You can just take a screenshot and then we'll move forward. So now let's start and discuss about this, right? I hope you've got this point. Now I'll make you understand this with an example as well. See, let's take an example. Let's take an example of a iron ore. Okay, so you have Fe2O3 ore with impurities of SiO2. Okay, so I am telling you that this is your impurity. Perfect. Now what will happen is, my dear students, that you will heat this complete ore in a container. Okay, yes, so we'll heat this in a complete container. Yes, ma'am. Just a second, I have to close this door. Okay. Okay, so now we can start again. Okay, the door has be opened again, so I don't know what is the problem, but now we'll have to discuss this like this. So you have Fe2O3 and you have SiO2. You heat it in a refractory funnel. Okay, so what will happen, ma'am? We know that you have an impurity which has a very high melting point. This impurity has a high melting point, my dear students. Okay, so what will happen? Fe2O3 will melt, so you will get your metal somewhere here. Metal you will get here in the melting form. So I'll write it as melt. And since your impurity hasn't melted, so it will be above it. Yes, ma'am. So your impurity would be somewhere here. right? Yes. So now like this, they form different layers and you can remove the impurity. Now, how are you going to remove this impurity? I'll give you a chemical reaction for this as well. Now, my dear students, what happens is you add one more thing to it, which is called as calcium carbonate, which is CaCO3. Okay, yes ma'am. Now what will happen, you know that when you add CaCO3, it is a group 2 carbonate, right? Yes, group 2 carbonates gets dissociated. Yes ma'am. So CaCO3 will decompose, my dear students, because you are heating it. Yes ma'am. So it will be converted into calcium oxide and CO2, right? Yes. So what will happen is that CaO is now you have calcium oxide and you have what? SiO2, which is your impurity. Now this SiO2 actually reacts with calcium oxide and it gives you CaSiO3. It gives you CaSiO3, which is called as slag. This is called as slag. This calcium oxide acts as a flux. This acts as a flux. This is your impurity, so you don't have a issue here. Now, my dear students, what has happened? Now we are going to discuss about this. You needed to remove this impurity. This impurity was SiO2. How did you remove it? You added calcium carbonate here. Calcium carbonate got converted into calcium oxide and carbon dioxide. This carbon dioxide just got escaped. Okay. Now, this calcium oxide actually reacted with your SiO2 and it gave you CaSiO3. Perfect. Yes. And this can be removed very easily. So how did you remove the impurity? Using this process. Now you still have your metal oxide in the melt. So what will happen? Now you have this Fe2O3 melt. You will reduce this with calcium oxide. I told you calcium not calcium oxide, carbon monoxide, and this is a good reducing agent. This is a good reducing agent. So what will happen? This will reduce Fe2O3 to Fe and itself will get converted into CO2, and this is how you get your metal. This is how you get your metal, right? Yes. So this is a very common thing which is discussed in your NCERT as well, my dear students. So if you want to write it, please write it and then we'll move forward. So let's move forward. Now what will happen? We've studied this. Now let's move forward. The slag is the fusible compound. The slag is the fusible compound, okay, which is obtained by the reaction of the flux with the gangue. My dear students, what is gangue? Gangue is your impurity. I hope you understand this, that gangue we use for the word impurity. Perfect. Right? Presence in the ore. So flux plus gangue gives you slag. Flux was calcium oxide. Your gangue was, I guess, SiO2 and you got CaSiO3. Now, the gangue may be of two types, my dear students. It could, the gangue the impurity which you are looking for, you don't look for impurity, you have it present somehow, but it could be acidic or it could be basic. So the gangue actually decides your flux. If you have a basic gangue, if you have a basic impurity, you use a acidic flux. If you have a vice versa, basically, right? Yes. So it could be acidic in nature, such as silica, FeO is etc. It could be acidic in nature. FeO is not basic, acidic. FeO is basic, right? Yes. So, or then calcium oxide, then you use calcium oxide because it is basic in nature. Because SiO2 was acidic in nature, my dear students, you used calcium oxide which was basic in nature, okay? But what happens? What will happen? You got CaSiO3. If you had a basic impurity or gangue, let us say FeO, if you had FeO as your impurity, so this would be your gangue or your impurity, and this is basic. Then, my dear students, you will have to use a flux which is acidic in nature. So now here SiO2 will act as a flux. It will act as a flux and then you will get FeSiO3. Okay, so it depends that what is your impurity, and or depending on that you use a flux. Here if I tell you, then this was your gangue This was your gang and this was your flux, which was basic in nature. Okay, so I hope you got this point. Perfect. Let's move forward. I know there are a lot of things to grasp. So watch this lecture in parts so that you get each and every point. Once you start feeling bored, please pause the video, have some rest, take a break, and then come back for again. Okay, so now basic in nature such as calcium oxide or magnesium oxide, you have, let us say, this acidic impurity. Why have they called it as an acidic impurity? My dear students, this is your flux and this is acidic in nature. This is acidic in nature and this is basic. Okay, I think there is some typing error. So if you have this impurity, then you have to take it acidic. Okay, yes, so make this correction. Let's move forward. Now, we've discussed everything, right? We've discussed calcination, we've discussed roasting, we've discussed even a complete example of Fe2O3 purification, extraction. Now we are going to talk about purification. You've got your metal, but still it's not pure. You have to purify it. Still there are a few impurities which are to be removed. So this is your step 3. So we've reached to the step 3, which is your purification process, right? So the purification is done after the extraction of metal. Once you've extracted the metal, now you will purify it. The metal extracted may contain some impurities still, so you have to remove them. Perfect. Let's move forward. The first is your refining. How do you remove the impurities which are still left? So some metals have impurities which are oxidizable, which are volatile. So what do? You just oxidize them in air. What will happen? The impurities will move away because they are volatile. They'll move away in the form of their oxides. Okay. So in this process, the crude metal is melted and air is blown through the metal. Perfect, no issues. As the more basic impurities are easily oxidizable, they are very easily oxidizable. They are readily oxidized by O2 of the air. No issues. The volatile oxides thus formed escape and the non-volatile oxides float on the molten metal. Right? Yes, as scum, which are removed, a small portion of the metal may be oxidized in this process. A few metal might also get oxidized and might also get removed, but still we'll get ample lot of metal. Perfect, yes. So this was very basic, very easy. There was nothing unique about this process. Now, unique processes are going to be discussed, and that is a polling process. So now we are going to talk about a polling process. Okay, so polling process, first and the most important thing is where this process is used. This process is used for the purification of majorly copper and tin. So I'll discuss copper with you. Similarly, it would be for tin. Okay, I'll give you an example for polling process. What happens, I'll give you all these steps as well. So my dear students, you have a lot of processes. You know that copper, let us take an example where you get copper in the form of CuFeS2. Okay, you get copper in the form of this. So in this ore, you have pure copper, you have copper, and you have various impurities. Let us say As, you have Sb, you have sulfide impurity as well, and you have iron impurity as well, and you have copper oxide. You have copper in the form of copper oxide as well. So this CuFeS2 actually contains a lot of things. Now in these, I can classify the various impurities as, just have a look. These impurities are actually volatile. These are actually volatile. This is less volatile. This is very less volatile. Okay. What does this mean? That this iron will get converted into oxide, but you cannot remove it. Okay. And you have calcium or copper oxide present. Perfect. Now, what will happen? First and the most important thing is you will do its concentration. This is your ore. You will employ the concentration process. I told you how do you do concentration of sulfide ores. I hope you know. So you will first do its concentration. Yes, ma'am. This would be our first step. After this, what will you do, my dear students? Second step, extraction of metal. You will do extraction of metal. Yes, ma'am. And third step would be purification. So we've reached here. So now, when you were purifying it, you got your copper. Yes, ma'am. Because you've extracted the metal, you have these impurities present. Still, you have these impurities present. So what will you do? First, and the most important part is that the step you used first. You will oxidize it. You will heat it in the presence of oxygen. Okay. So when you will heat it in the presence of oxygen, so I'll write here, we'll heat in the presence of, or I could say we'll do thermal refining. We'll do thermal refining. What was thermal refining? Heating in the presence of oxygen. Okay, so what this will do? This will convert these volatile oxides and these will escape. So volatile oxides will escape. Okay, so what do I mean by that is, these three AS, SB and S in the form of their oxides, they'll get escaped. Okay, so now in your solution, what is left? Ma'am, I have copper, I have Fe and I have copper oxide. And also remember that this Fe has now converted into FeO. Okay, so now you have this. What will happen now? Now what is going to what step is going to take place? You will have copper, you have FeO and you have CO. So now, my dear students, what happens is, you have this container. In this container, you have Cu, you have FeO and you have CuO. So what happens is, in this container, there is silver, there is lining of SiO2. There is lining of SiO2. So this means that there are a few poles, my dear students, like these. These are made of SiO2. These are made of SiO2. So you know that FeO is your impurity. Yes. So if FeO is your impurity and FeO is basic in nature, so I can call it gang. And I can say that this is basic in nature. So what do I need? What do I need? Ma'am, you need a flux which should be acidic. And what is the flux that is acidic? I have added SiO2. See? SiO2 lining. Yes. So I have added this, which is acidic flux. Okay. Now, this will give me FeSiO3, which is my slag. So I'll get slag. Yes, and I can remove it. So in this way, FeO will get removed. In this way, my dear students, FeO will be removed. FeO will be removed. So what can I say? This is how FeO is removed. Now what are you left with? Now you have copper and you have copper oxide. So now you need copper oxide's oxygen to be removed somehow. So how are you going to do? How are you going to remove this and get pure copper out of it? You use green wood poles. So next step would be using poles of green wood. So what happens is when you use this green wood poles, which is made of carbon, my dear students, when you heat them, you actually get methane. Okay, when you heat these poles, green poles of these poles of green wood, its carbon get converted into CH4. You need not understand how it got converted into CH4. You only need to understand it that when you have green wood poles and when you heat them, they get converted into CH4, methane. Okay, now this methane will react with CuO and you will get Cu and you will get CO2. This is your pure copper. And this is how you get your pure copper. And this process is known as polling. This process is known as polling. Okay? Yes. So I hope you got the polling process. Okay? What did you do? You first concentrated the solution, then you extracted the metal, and then you got this. There were these impurities which could be removed by thermal refining. Now if you talk about iron got converted into iron oxide. I know it is an impurity, so I have to add a flux should be acidic in nature because the oxide is basic. So I formed a slag, formed a slag and I removed that. Now I had to remove the other impurity as well. So I used greenwood poles, I heated them, I got methane out of it, and I used that methane which reacted with CuO, and I got the pure copper. And this is how poling process is used. So I hope you got this very good, my dear students. Let's move forward. Next is your fractional distillation. And similarly, my dear students, I hope you get this. Now you can write here that similarly for tin. The same process is used for tin. Okay, I hope you got it. Now we'll move forward. If you talk about fractional distillation, what happens in fractional distillation is you have a metal and you have impurities. Okay. Now, imagine you have impurity and metal, and let us say that your metal is very volatile. It is very volatile, its boiling point is very low. Okay, so what will happen? You have melted it and you use this setup. So what will happen is, here is your metal plus impurities in the liquid state. Here is your metal and impurity in the liquid state. You heat them. Yes, ma'am. Since here I know that boiling point of metal is less than boiling point of impurity, so your metal will boil first. I hope you get this. Your metal will boil first. Yes, ma'am. Now when it will boil, it will get converted into its vapor forms. Yes, ma'am. And your metal will escape through this in the form of air. Yes, ma'am, in the form of vapor. And you have used this setup that your vapor will come here, and you are using it as a condenser. So what do? You boil it, your metal gets converted into vapor form, you collect its vapor here, and then you condense them, once you've condensed them, you will get your metal here, and your impurities would be left far here. So what does fractional distillation do? It uses the concept of difference in the boiling points of impurities and your metal, right? I hope you got this. Now we will read this. In this process, the crude metal is subjected to fractional distillation when the impurities having lower boiling point. Okay, they have considered here that impurities have lower boiling point. I have made you understand it with the help of metal has a lower boiling point. Out of the two, any one can have lower boiling point, that will be removed there, and you will get the other part this side. Okay, so here they have used the part where impurities have lower boiling point. Okay, so impurities having lower boiling points than that of the metal distill off first, leaving behind the pure metal as the residue. So if you want, you can use this concept as boiling point of impurity they have used less. But if it was the other way around, that would also have worked. Okay, yes. So if the boiling point of the impurities are found to be greater, see, now this is the other part. If the impurities is found to be greater than that of the metal distills of the first, which is collected in the condenser, the impurities are left behind residue. Okay, where is it applicable? To D block elements group 12, for example, zinc, cadmium and mercury. So this is important for you. You need to know that where you can use a particular process. So I hope you got this point. I hope you got the part of fractional distillation, right? Yes. So if you know the process and you are given a option, I know you can do that particular question very easily. We'll practice questions as well, don't worry. Now let's move forward. Refining. In refining, next process is liquation method. Where liquation method is used, my dear students, zinc, lead, SN, bismuth, etc. Metals are purified by this method. This method is used to purify those metals which have low melting point and the impurity present has high melting point. Now what does this liquation process do is, the condition which is used here is that that the metal has lower melting point than the impurities present. Okay, so the condition is that metal melting point is less than the impurities melting point. Okay. Impure metal is heated and inclined earth way. Metal melts and flows down the group. Now what happens is very easy. Do we have a picture? Just let me see. Yes, we have a picture as well. So what will happen, my dear students? You will uh, throw your melt here. Okay, now you know that out of metal and your impurity, metal has a lower melting point, so it will melt first. As your metal melts, it flows and you get pure metal first, and impurities will melt later, and so they will come later. So this is how you remove the two. Very easy, right? Yes, so this is how you remove it. Perfect. I hope you got this. This is the major condition which you need for liquation process. Perfect. Let's move forward. Zone refining, very important, my dear students. What does zone refining do? In zone refining, what the condition is used is, I'll give you a very basic layman language idea and then we'll read the theory. What happens is that you have a metal, which is present with impurities. Now, what is the major condition that is required is that the impurity is actually more soluble in the molten state of metal. This means that if your metal is melted, then impurities are more soluble in that as compared to the pure metal. Okay, yes. What happens is, let us say you have something like this. Okay, now you have a heater here. You have a heater here. This is a impure metal. This is a impure metal. So now what will happen, my dear students? You have to try your imagination out here. This heater will keep on moving. This heater will keep on moving from here to here to here, here. Okay. As the heater will move, obviously here your impure metal will melt. Yes. And then when this heater will move forward, this part would start melting and the back one part would start crystallizing, condensing, that is crystallizing again. Right, yes ma'am. So the impurities which were present here, what is going to happen is that the impurities are more soluble in the molten metal. They are more soluble in the molten metal. Yes ma'am. So what will happen, my dear students? When this metal will start crystallizing and this metal will start melting because the heater is moving like this, what the impurities will do? The impurities present here will move here because they have a tendency more to get soluble in the melt. Okay. Similarly, now there will be a lot of impurities here and the heater would move here now. What will happen? The impurities present here will move this side and they will be soluble in the melt again. This way the whole process takes place and you start getting pure metal here. Okay, and finally you get all the impurities at the end, and what do? You cut off this part, and this is how you get a pure metal. And here, my dear students, by zone refining you get the most purest form of the metal. Right? So this is how your zone refining is used. And the most important thing is that zone refining is used where the purest form of metal is used, that is your semiconductors. In semiconductors you need pure form of metals, so all the semiconductors are actually purified by this method. Okay, yes, so this was the gist. I'll show you the apparatus as well. First read it. This process is based on the fact that the presence of impurities lowers the melting point of a metal. You should write that it has a tendency of getting more soluble. This is written in your NCERT as well, that the impurities have a tendency to be more soluble in the molten state of metal. Consequently, the impure molten metal on resolidification, the pure metal first crystallizes out, leaving behind the impurities in the molten metal. Okay, yes. It is used to get ultra pure metal used as semiconductors. Condition is melting point of metal is more than melting point of impurity. This is important. This is the condition you need. And impurity lowers the melting point of the metal as well. Okay, now let's see the setup. So this is the setup. Just a second, my dear students. Just a second. Mic issue. You just see the setup. I hope I'm audible. Okay. Fine. Okay. So now what happens is, this is the setup and you have this heater here. So what will, this heater is movable. So what will happen? You will keep on moving this. You will keep on moving this. First, this part would be melted, then it will crystallize and this part will be melted, and then this will be crystallized and this part will be melted. And what will happen? The impurities will keep on moving towards the melt. Similarly, this will keep on moving, and finally you will get all the impurities here, and you can cut that impure part and you will get the pure metal there. Perfect. So what is happening here? You have recrystallized pure germanium semiconductor. You have the circular heater here. You have impure germanium rod this side. Okay. Direction of travel of heater, molten zone and impurities. Perfect. And zone refining of germanium metal. So this is how you purify the semiconductor metals. Perfect. Thermal decomposition method. Now we are going to talk about a few thermal decomposition methods, my dear students. What do? You actually take the impure metal, you convert it into a complex, which complex has the tendency to decompose. Okay, so once you will convert it into a complex, it will be decomposed into a pure metal and the other part which contains the impurities. So in this method, the impure metal is converted into a suitable volatile compound. On heated gets decomposed. It gets decomposed to give pure metal. Some examples of thermal decomposition method are given below. Okay, so it is applicable for titanium, zirconium, thorium and vanadium. Perfect. Now, Mond's process. There is a process which is basically known as Mond's process, also called as carbonyl process. Where is this applicable, my dear students? It is applicable for nickel, where you react nickel with 4 carbon monoxide and you get the complex nickel carbonium. Okay, you get this complex. This complex is volatile. Now on heating this will be decomposed. So what do? You decompose the complex and you get nickel. Now this nickel will be pure and you will get this impure carbon monoxide, which you need not worry about because you needed pure. But this nickel was impure, my dear students. This nickel was impure. Perfect? Yes. Similarly, von Arkel process for refining zirconium or tin. Okay, what do? You have zirconium, you react it with 2 iodine, you get ZrI4. Now you decompose this, you get zirconium and you get this. Now this is pure and this is impure. Perfect? Yes. So this is how the process takes place. So I hope you got this process also. Very good, my dear students. Let's move forward. Next is your electrolytic process. What happens in an electrolytic process? Let's discuss about it. You might have studied this in the electrostatic chapter, electrochemistry chapter as well, right? What happens is you have 2 types of electrodes. I told you, you have one anode. And you have a cathode. Perfect? No issues? Yes, ma'am. What happens on anode is always and always oxidation. And what happens at cathode? Always and always, ma'am, reduction. Right. Perfect, my dear students. If you talk about anode, it is made of impure metal. It is made of impure metal and this is made of pure metal. So what do? You make 2 types of electrodes. You take 2 types of electrodes. One is your impure electrode and one is your pure electrode. Now, in anode, I told you oxidation takes place. Oxidation is loss of electrons, right? So if I write a oxidation reaction, let's write for copper. So what will be the oxidation of copper, ma'am? It will get converted, copper will get converted into copper 2 plus 2 electrons. This is oxidation reaction. And what will happen in reduction? This Cu2 plus will take 2 electrons and it will get converted into copper solid, because reduction is gain of electrons, right? Yes. So now, since this is what a container will have your anode and it will have a cathode. So ma'am, I know that this is a copper electrode, it is getting converted into copper 2 plus, that is copper 2 plus ions, right? These copper 2 plus ions will take 2 electrons and get converted into this, they will get deposited on the cathode. So slowly and slowly cathode will keep on increasing, it will keep on thickening, right? Yes. And this is how you get the pure metal. You take the impure electrode and you get converted into a pure electrode. Okay, yes. So now you can read this. Copper, silver, gold, lead, etc. are purified by this method. It is an important method for the purification of metals. Pure metal is made in cathode and impure metal anode. Aqueous solution of a salt of the metal acts as electrolyte. Obviously you need electrolyte, and I hope you know that whenever you talk about the electrolyte, it will be the aqueous solution of that metal only. So you have anode, impure, cathode, pure, and electrolyte is aqueous salt solution of that particular metal as well, right? Yes. So you can write this and then we will move forward. Okay, so now let's move forward. Now what we are going to see? Now we are going to practice some questions. Okay, yes. Just a second. One thing is left, my dear students. Yes. Now, one very important point to remember is that while this all takes place, while this purification takes place, what happens is, obviously you have an anode which is impure and you have a cathode which is pure. So where are the impurities? My dear students, the impurities actually settle down here below the impure metal, that is your anode. Below the anode, the impurities such as silver, gold, etc., settle down here, and this is known as, and my dear students, this is known as anode mud. This is known as anode mud. I'll just erase it and I'll write it as anode mud. Okay. So if we talk about the impurities, then the impurities mostly contain silver, gold, etc. And these impurities actually settle down below the anode and you get anode mud, right? Yes. So this is how you are going to purify any metal. Perfect. Let's move forward. Now, when we talk about the questions. So here is a question, my dear student. First question is, when the sample of copper and zinc as impurity, so you have a sample where you have zinc as a impurity to be purified by electrolysis, the appropriate electrodes are, what will be the appropriate electrodes? Ma'am, I know that I have zinc as an impurity and I want pure copper. So I don't have to think about the impurity. You only and only have to think about copper. So you will have anode and you will have cathode. And I know that at anode I get impure sample, impure metal, and at the cathode I have the pure metal. So you need not worry about the impurities. You only have to think about the metal you are purifying. Okay. So if I see the options, I can say that cathode will be pure copper and anode would be impure sample. So option D will be your correct answer. Okay. Let's move forward to the next question. Next question says that during the process of electrorefining of copper, some metals present as impurities settle as anode mud. These are, which impurities settle as anode mud? I told you that mostly these are your silver and gold impurities, right? So silver and gold, that is option C, will be your correct answer. Okay, let's move forward. Next question, my dear students. You are provided with samples of some impure metals, such as you have some impure metals, such as you have zinc, then you have copper, and then you have germanium. Okay, so I'll write GE. Perfect. Which methods would you recommend for the purification of these metals? Pause the video and try this question yourself and then we will move forward. So if I talk about zinc, what will happen? So ma'am, if you talk about zinc can be, how can you purify zinc, my dear students? if you are provided samples of some impure metals such as zinc, copper and germanium. So I think zinc is a, my dear students, which metal? Ma'am, it is a D block metal. Yes, and D block metals can be purified by, my dear students, distillation method. Don't forget that while distillation I talked when I talked about distillation, I told you that mostly the D block elements are purified by this method, right? So I can say distillation. Perfect. Let's move forward to the next part, which is copper. How can you purify copper? By electrolytic refining. So I can say that this can be purified by electrolytic refining. We just talked about it. No issues. Perfect. Now let's move forward to germanium. Germanium is a semiconductor. It is used as a semiconductor, right? And when we talk about semiconductors, we want the ultra pure kind of metals. And when you want ultra pure kind of metals, my dear students, you use a zone refining process. You use zone refining process. Okay, yes. So this is how you can purify each one of them. So these type of questions are generally asked, and I hope if you know the concept, you can do these questions. Now let's move forward to the next question. Why graphite is used as anode but not diamond? See, my dear students, you talk about anode, you talk about cathode. Obviously, what is happening there? Ma'am, electrons are getting loose and ma'am, electrons are gained, right? Yes. So, my dear students, it needs to be a good conductor. It needs to be a good conductor. And out of diamond and graphite, I know that graphite have valence electrons. It has valence electron. It has free electrons. Better word to say, it has free electrons. Why? Because it has sp2 hybridization. One carbon forms 3 bonds, one electron is free. So, ma'am, graphite is a good conductor of electricity, but diamond is a bad conductor, and that is the reason that at anode we can use graphite, right? Yes, perfect. I hope you got this point. Now let's move forward to the next question. You have to pause the video and try the questions yourself. I hope you've not forgotten that. Now let's move forward to the next question. Question says that name one metal that is refined by each of the following process. Okay, a good question. You have to pause the video. I'm telling you again and again. Let's see. First is vacuum distillation. My dear students, if you talk about distillation, I know that D block elements are to be considered here. Yes. So I only remember one which I just recently studied, which is zinc. So ma'am, I'll write zinc. Perfect. No issues. Let's move forward. Mons process. What was Mons process? Ma'am, there we used to make a complex, and that complex we used to decompose and we used to get the pure metal. And if I talk about the Mons process, it was with nickel carbonyl complex. So we can purify nickel by this complex process. Next is electrolysis. Ma'am, in electrolysis, I remember one example very, very clearly, which was copper. We made impure electrode, we made a pure electrode. I hope you remember. So here I can write copper. One arcal process, my dear students, ma'am, zirconium, titanium, all these, right? Yes. So I can write zirconium, or you could write titanium. It used to make a complex with iodine, right? I hope you remember, exactly like Mons process. Next, zone refining. Ma'am, all the ultra pure metals, for example, the semiconductors which we use, those metals can be purified by this particular method. So I can write germanium, right? Yes. So this is how you're going to answer the questions. I don't think so you will have any problem now, right? Isn't metallurgy interesting? It is, right? Let's move forward. Next question. Okay, not next question. Now we are going to talk about the Ellingham diagram. Okay, so my dear students, I told you that you while you have a oxide after roasting and calcination, you get a oxide, and you can get the metal from there by reducing it with a reducing agent, and you get a metal. I hope you know that when you have a metal oxide, you use a reducing agent and you get a metal. I hope you remember this. Yes. So how will I get this reducing agent? The question is that how will I get this reducing agent? We are going to discuss about this. This reducing agent can be found out by the Ellingham diagram. Okay. So what is Ellingham diagram? Nothing. It is a plot of delta G. What is delta G? It is your Gibbs free energy. I hope you remember delta G you've studied in thermodynamics versus temperature plot. It is just a plot of various reactions. It is just a plot of various reactions of delta G versus temperature. It gives you various delta G values at various temperatures and you find out which is a better reducing agent seeing that Ellingham diagram. How to study that Ellingham diagram? That is my responsibility to teach you. Okay, so now we are going to study that. Perfect. So for this Ellingham diagram, we need to know something which is very important, and that is a very important thermodynamic reaction. Delta G is equal to delta H minus T delta S. I hope all of you know that when a reaction is spontaneous, if a reaction is spontaneous, that it takes place on its own, then ma'am delta G should be negative. Then ma'am delta G should be negative. And if a reaction is non-spontaneous, so ma'am, when will a reaction be non-spontaneous? That it does not take place on its own, ma'am, when its delta G value would be positive. Okay. So my dear students, if you need a reducing agent, then it should reduce very properly, and that means that its delta G value should be negative. Overall, a particular reaction's value, if it comes out to be negative, then you can consider that as a good reducing agent. Okay. Yes, so our aim is to find out the reactions whose delta G should be negative. Okay. Yes, ma'am. We know this. Please don't tell us this. We know this. When can be delta G negative? When can be delta G negative? You know that entropy change is always positive. I hope you know that change in entropy is always a positive value. Temperature can never be negative. Yes, ma'am, it will be a positive value. This means that this complete value is always positive, but since it has a negative sign, so it will always be a negative value. So whenever I talk about delta G for a endothermic reaction, delta H is positive, right? Yes. What do you need? You need high entropy. If you're not getting this, just leave it. You just understand that you need one thing, which is this value to be negative. If this is negative, then the reaction is spontaneous. Okay. Don't just leave thermodynamics on its own. We are only going to discuss about this. So I want this value to be negative, nothing else. Okay. So now we are going to study the Ellingham diagram. When you will open your NCERT, you will see something like this. You will see something like this. And everyone will be shocked and everyone will be confused as if, what is this, ma'am? How are we going to study this? I am here. Why to fear, right? Yes. So what will happen, my dear students, that when you see this Ellingham diagram, this is delta G values and these are the temperature values, right? These are your temperature values. So I hope you understand that okay, I'll make you understand this by one more important thing, right? What is that? See, if you talk about delta G, my dear students, delta G should be negative value. So if you see here, this is minus 1200 and this is minus 1100. Which value is more negative? The below one is more negative? Yes, ma'am, the below one is more negative. If you talk about a reducing agent reaction, I can say that metal oxide plus the reducing agent, let us say the reducing agent is X. Right? Yes, this is your reducing agent. This will give you metal and this will give you XO. This means that, ma'am, two things have happened here. This has reduced. Here reduction has taken place, but your reducing agent has actually got oxidized. Right? Yes, ma'am, this oxidation process has taken place. I want a negative value for both of these reactions so that my net delta G value is negative. Okay. So more the negative value of your reducing agent getting converted into its oxide, more the faster the reaction will take place. Right? Yes. So this means that here, my dear students, magnesium In this particular plot, you can say that magnesium is getting converted into magnesium oxide, okay, and here aluminium is getting converted into aluminium oxide. So if I say that magnesium is a better reducing agent, that means magnesium will get converted into in its oxide faster as compared to aluminium, which will get converted into its oxide. The reaction which has a better negative value, more negative value, that reaction will take place faster. I hope you understand this. More the negative value, more the spontaneous is the reaction. Yes. So if I ask you from both of these, which metal will get converted into its oxide faster? You will say obviously ma'am magnesium, because it's below, and since it's below it has more negative value of its delta G. Yes. So my dear students, which will be a better reducing agent? What is a reducing agent? Which reduces the other and itself gets oxidized. So ma'am, I see that magnesium is getting oxidized faster, so magnesium will act as a better reducing agent. So one concept, one conclusion that you can draw is, you can say that more the negative delta G value, better the reducing agent. Better the reducing agent. I hope you get this right. Second conclusion that you can draw is, more the below metal in Ellingham diagram is a better reducing agent than the above one. Okay, so you can write it in your own language as well, right? You can write that the metal below in the Ellingham diagram will be better reducing agent. Okay, I hope you got the concept. Huh? So if I ask you, out of aluminium and magnesium, which is the better reducing agent, you will say magnesium is the better reducing agent as compared to aluminium. Okay, so ma'am, magnesium can reduce aluminium, but can aluminium reduce magnesium? No, it cannot, right? So the below one can act as a reducing agent, the above one cannot act as a reducing agent for the below metal. Perfect, yes. But this whole story changes. Where, if you see at this particular temperature, let us say it to be 1250. Let's call it 1250. At 1250, what is happening is, ma'am, before 1250, magnesium line is below and aluminium line is above. So this is acting as a better reducing agent. But ma'am, after 1250 degrees Celsius, you see that this magnesium line is going here, and this aluminium line is here. So now my dear students, aluminium line is below and magnesium line is above, right? So at this point, this aluminium is getting converted into aluminium Al2O3, okay, and here this is getting converted into MgO. So ma'am, at this point, that is above 1250, which is a better reducing agent? Now ma'am, aluminium is a better reducing agent, and aluminium can reduce magnesium. Now magnesium cannot reduce aluminium. So everything depends on the delta G value as well as the temperature. So whenever you are given an Ellingham diagram, you have to see that which value, which line is below the other. At the same time, you have to see the temperatures as well, because at different temperatures, different metals act as better reducing agent. So after 1250, aluminium will act as a better reducing agent as compared to the magnesium. And now aluminium can reduce magnesium, but magnesium cannot reduce aluminium. This is the most important part of Ellingham diagram. This is the gist of Ellingham diagram. Similarly, if I ask you a question that aluminium can be reduced by, give me an answer to the question. Aluminium, okay, I'll write it with, aluminium can be reduced by, you have options. Let's say you have option as Fe, you have zinc, you have magnesium, and you have Mm, okay, copper, and let's say the temperature is below 1200 degrees Celsius. Below 1200 degrees Celsius, my dear students, aluminium can be reduced by, let's see. First of all, the most important thing is below 1200. So, ma'am, I know that I have to draw a line at 1200. So, let's draw a line at 1200. Okay. We've drawn a line at 1200. Okay. Now, I have to see here. Okay, just a second. Okay. Now, tell me. Aluminium. So this is aluminium. If I want to reduce aluminium, I need a reducing agent which has a delta G value even negative than aluminium. So if I see, first option is iron. Iron is above aluminium, so it cannot reduce it. Next option is zinc. Zinc is again above aluminium, so it cannot reduce this. Third is magnesium. Magnesium is below this, then yes, it can reduce. So magnesium is the correct answer. Copper cannot remove because again, ma'am, reduce because it is again above the line. Perfect. Yes. So this is how you're going to read the Ellingham diagram. Can we do some questions? Let's solve some questions. So here is the question. Is this a question or what? Okay. We'll read it. We'll study it. It is not a question. We only have to discuss this part. Okay. Now, my dear students, you can say that below 1073 Kelvin temperature. Below 1073 Kelvin temperature, iron can be reduced by, see, this line is for iron. So this line is for 2CO. I'll write it with another color. 2CO plus O2, and this will give me 2CO2. Okay. So I can say that for iron below 1073, below 1073 Kelvin temperature, I can say that iron can be reduced by, iron oxide can be reduced by, my dear students, ma'am, it can be reduced by carbon monoxide. So I can say that iron can be reduced by carbon monoxide. Yes. Why? Because below 1073 Kelvin temperature, this line is below Fe. Perfect. I hope there's no issue. Now let's move forward. Iron oxide. Okay, FeO. Now let's move forward, because obviously if it is oxide only, then you can reduce it now. Yes, ma'am. So iron oxide can be reduced by carbon monoxide. Now above 1073 Kelvin temperature. What will happen above 1073 Kelvin temperature? See, now you have crossed the temperature. Now if you see, this line is for iron oxide, this line is for FeO, and now the carbon monoxide line has gone above, and ma'am, carbon line has came below. So above 1073 Kelvin temperature, FeO can be reduced. FeO can be reduced by carbon. FeO can be reduced by carbon, right? Yes. So this is how you can find out which one is a better reducing agent at a particular temperature. Now let's solve some questions. Okay. So here is the question, my dear students, and the answer is written here again. I don't know what is the issue, but okay, now you've seen the answer. What can I do? So see the question. Considering Ellingham diagram, which of the following metals can be used to reduce alumina? It is the same question that ma'am asked. So this is fine, ma'am. We know that the answer is magnesium, and even the options are same. Whoa, what a coincidence, right? Yes. Let's move forward. Next question, my dear students. You have a question. Now you have to answer this very quickly. Pause the video and try the question yourself first. Okay. So the question says that the Ellingham diagram for zinc, magnesium and carbon converting into consequent corresponding oxides is shown below. You have been given a Ellingham diagram. So you have to answer. The first question is, at what temperature zinc and carbon have equal affinity for oxygen? You have to tell that zinc and carbon has equal affinity, that is they should intersect each other. Yes ma'am. So let's see, zinc reaction is here, this is the zinc reaction, and which is the carbon reaction, this, where do they cross each other? It is at 1000 degrees Celsius. So ma'am, 1000 degrees Celsius, option A is the correct answer. Let's move forward. Next question. To make the following reduction process spontaneous, now you have to make the reaction spontaneous, that is you need delta G to be negative. Temperature should be, what should be the temperature? Now you are actually, what are you doing? You have a zinc oxide and you are using carbon as a reducing agent. So you need a temperature where carbon should be below zinc. Carbon should be below zinc, only then carbon can act as a better reducing agent. Okay, so if I talk about carbon, then my dear students, at this temperature zinc is below carbon, so this cannot act as a reducing agent. But once they cross each other, now this line is for zinc and this line is for carbon. Here ma'am, carbon is below zinc, here it can act as a reducing agent, right? So the temperature should be more than 1000 degrees Celsius. Let's see the temperature which should be more than 1000 degrees Celsius. If we see more than 1000 degrees Celsius, or the option is more than 1100 degrees Celsius, which is the most correct option. So ma'am, option B is the correct answer. Okay, now let's move forward to the next third question. At 1100 degrees Celsius, which reaction is spontaneous to a maximum extent? You have to tell which is the most spontaneous reaction. For most spontaneous reaction, you need delta G to be negative. Okay, yes. So let's see, for 1100 degrees Celsius, which reaction is the most spontaneous? Okay. This means that if we see magnesium oxide is getting reduced by carbon, this is getting, this line and this line never ever is happening there, that carbon line is coming below magnesium line. It is not happening in this particular part. So ma'am, first option is entirely wrong. Let's talk about the second option. You have zinc oxide and carbon. If you talk about zinc oxide and carbon, my dear students, yes, it reduces, but it has a very less negative value of -600 at a very high temperature. It is talking about 1100 degrees Celsius. Yes, it is possible. It is possible. But ma'am, value is nearly -600 around. Okay, so it is not very negative. So yes, this is a possibility. Let's just leave it. Let's talk about the other part. Magnesium oxide and zinc. You have magnesium oxide and zinc. My dear students, yes, they act as reducing agent, zinc, but at a very high temperature, and the value is again -600, around -600. Okay ma'am, so here also the value is -600 around, here also the value is -600 around. Okay, so this is also possible. Let's talk about D. ZNO, your ZNO is reduced by magnesium. It is reduced at very low temperature, and even the delta G value is -1000 degrees Celsius. Sorry, -1000 kilojoule. Right? Yes. So ma'am, I can say that the most negative value is coming out for the fourth part. So option D will be my correct answer, because it said that it should have the maximum extent, to the maximum extent, and maximum extent means that delta G value should be the most negative value, and that is your option D. Right? Yes. So this is how you are going to solve the questions based on the Ellingham diagram. Perfect. Let's move forward. Next question. Now you have few questions which you have to solve. Okay. Perfect. First question is, which of the following metal is leached by the cyanide process? Now you have to tell me, my dear students, this question you can answer only and only by reading NCERT. So for this, you need to read the NCERT. You know the leaching process. I have discussed the leaching process with you for aluminium. Similarly, there is a small part which has discussed in NCERT. You have discussed about the leaching part of silver as well, okay, where you use cyanide. So here I am telling you that option A is the correct answer, but you need to read the NCERT for this particular question, okay. Yes, one part I have discussed, the other part you have to discuss, you have to read, so that you do some sort of a work. Okay, so now let's move forward. Next question, my dear students. Semiconductor materials like silicon and germanium are usually purified by ultra pure metal zone refining. Yes, so ma'am, option B will be our correct answer. Very good. Let's move forward to the next question. Next question. The most electropositive metals are isolated from their ores by. It was in the starting of the chapter that we discussed this part. It is purified by the electrolysis of fused ionic salts. Okay, it is extracted by the electrolysis of fused ionic salts. So option D will be your correct answer. This was in the starting of the chapter. Okay, yes, perfect. Let's move forward. Next question. Hematite is concentrated by. See, my dear students, this is a very important question. We have actually discussed it. If you know what is hematite, then you can solve this question. If you don't know hematite, you cannot solve this question. Okay, so I'll tell you, hematite is a ore of iron. Hematite is a ore of iron. Okay, this is a hint. Now you have to give the correct answer. Pause the video, try the question yourself. Okay, so this will be a homework for you, my dear students. I have given you the hint. In fact, I think most of you know the answer as well. So let's see, give me the answer in the comment section. Okay, so this is going to be your question, homework question. Let's move forward to the next question. Next is cinnabar is the ore. O-R-E, ore of. Cinnabar is the ore of. Again, I am telling you, you need to learn that table of the ores. Okay, so my dear students, cinnabar actually is HGS. Mercury sulfide. So it is an ore of mercury, Hg. So option C is your correct answer. Okay, perfect. Let's move forward to the next question. Next question. Blister copper is. My dear students, when you will read the NCERT, again NCERT, I am actually promoting NCERT here. When you will read NCERT, there I have discussed a process of purifying copper with you. Yes, there you will read a term which is known as blister copper, and that blister copper actually means your impure copper. Okay, so to impure copper you actually call blister copper. So blister copper is impure copper, option D. So for all these terms you need to read the NCERT, I am telling you. Okay, and now you'll understand NCERT, I assure you that. Perfect. Now let's move forward to the next question. Froth flotation process is used for the concentration of ore of. Froth flotation is used for the concentration of sulfide ores, right? Yes. So ma'am, sulfide ores, and which sulfide ore have we discussed? I hope you remember. We have discussed PBS sulfide, we have discussed zinc sulfide. So ma'am, I can see that option D will be my correct answer, right? Yes, perfect. Let's move forward to the next question. Copper is extracted from sulfide ore using. Now it is saying that copper is extracted from the sulfide ore using. So now my dear students, copper can be copper, one process we have discussed about copper in n number of ways, and I told you that one metal can be extracted in different ways. So you have to see the options. So copper is extracted from sulfide ores by the method. Now let's see. Carbon reduction, carbon monoxide reduction. Have we discussed the reduction processes with copper? No ma'am. Copper, my dear students, actually can be obtained by auto reduction method. It can be obtained by auto reduction method. Okay, so option C will be your correct answer. That is, you have a copper sulfide, you have a copper oxide. What will happen? You have Cu2S, you have, let us say, CuO, you get copper, and you get SO2. You can have Cu2S or you can have Cus. So this gives you copper plus SO2. So this is known as self reduction. This is known as self/auto reduction. Okay. So you get pure copper like this. Perfect. So this is known as auto reduction. Okay. Let's move forward to the next question. Next question is, main function of roasting is. What does roasting do? It forms oxides. Yes ma'am, it forms oxides. Perfect. To remove the volatile substance, to convert the ore into the oxide. So my dear students, when you talk about roasting, it is a method of extraction of metal. If you are extracting the metal, this means that you are extracting the metal. So to remove the volatile substance, to remove the metal, yes ma'am, roasting is the process of extracting the metal. So first option is correct. Also, how do it extract? It extracts by forming it into the oxide. This means that both A and B, that is option C, will be your correct answer. Okay, yes, so I hope you get this point as well. Now let's move forward to the next question. Sulfide ores are common for the metals. The more you will read NCERT, the more you will be able to answer the questions. Okay, so if I see, then I can say that I have heard of AGS. I have heard. I have heard of zinc sulfide. I have heard. I have heard of PBS as well. So the three sulfides which I have heard is option A. So option A is your correct answer. So these are the questions which will come to your mind only and only once you've gone through the chapter completely and thoroughly. Perfect? Yes. Let's move forward to the next question. Next question is, select the reaction in which SO2 is not evolved. Now, my dear students, you have to give the reactions in which SO2 is not evolved. Okay. So, let's see which is the correct option. If I see the first option, this is Cu2s is roasted. If I roast Cu2s, this means that in the presence of oxygen, I am heating Cu2s. So, I'll get, this is plus 1, this is 2, so I'll get CuO plus I'll get SO2, right? Yes. So, ma'am, in the first reaction, SO2 actually is evolved. Perfect. So, this cannot be my option. This is A. Next is Cu2s is heated with roasted Cu2s. So, now, my dear students, for roasted Cu2s, you have already written the reaction. Okay. So, for second part, half reaction would be this. After this, what you are doing? You are heating the Cu2s. You are heating the Cu2s again. So this means that once you heated this, some of Cu2s is still left. And now this has to react with CuO. So now this will react with CuO, and what will you get? You will get copper and you will get SO2. And ma'am, this is actually known as auto reduction. You told me that this is actually known as auto reduction. So copper got auto reduced into copper and SO2. So ma'am, in second process as well, I got SO2. Perfect, no issues. Now, third is FES is partially roasted. Now, my dear students, for third C part, if you partially roast FES with O2, obviously O2 in presence of oxygen, so what will happen, ma'am? You will get iron oxide and you will get SO2. You will get SO2. So, ma'am, here also SO2 is evolved. Fourth is partially roasted FES, means for this particular part, this reaction is valid. Partially roasted FES is heated with silica. What is silica? SiO2. Okay. So, when you partially roast this, what do you get? You get FeO. You get FeO, and this FeO will react with SiO2. What will happen, my dear students? When FeO reacts with SiO2, what do I get? I get FeSiO3. Do I get SO2 here? No, ma'am. So this is your D part, and in D part, SO2 gas is not evolved. SO2 gas is not evolved. So, ma'am, option D will be my correct answer. Only and only this is the part where SO2 is not evolved. Okay. So I hope you got this point. This was a very good question and it actually cleared all your concepts regarding metallurgy. Clear? Yes. Perfect. Let's move forward. And with this, we have came to the end of our session. So I hope, my dear students, you actually got all the processes, and now I would advise you to learn these processes in a story type. If you will study these processes with a lot of burden that I have to memorize these, I have to mug up these, then you will never be able to enjoy metallurgy. If you want to enjoy metallurgy, study this particular chapter in bits, and also try to make a story out of it. Only then you will be able to excel metallurgy. So I hope you got this point. I hope you were able to answer the questions. I hope you were benefited by this particular session. Do let me know in the comment section, and thank you so much for being here, for attending this session, and we'll meet in the next session. Till then, keep studying. All the very best.